So there's two types of symmetry we're going to be asked about. A shape can have lines of symmetry, or it can have order of rotational symmetry. And I want to I want to show you both. And it's not always what you think. So if you take a shape like a rectangle, an axis or a line of symmetry is one like these red dotted lines that we've drawn here. If I were to cut out that shape and fold it in half, it would match exactly together. That's what symmetry is. So that rectangle has one, or any rectangle has one line of symmetry and another line of symmetry there. And if I cut that out and I folded it in half, they would match up exactly. There'd be no overlap, and so we say both sides are symmetrical. We're tempted to think, well, if I put a dashy line through there, well, that's probably a line of symmetry too, and it's not. Because if I folded this part over here, I'd end up getting a sticky outy bit. They don't overlap exactly, so no. So a rectangle has two lines or axes of symmetry. Something like this, where we have an isosceles triangle, where it's got two long sides and then a side that's another length, only has one line of symmetry or axis of symmetry, because there's only one line that we can draw, that red line, where we could fold both sides over. If I tried to draw a line like this, they're not going to match up. Sorry. Now, something similar is called the order of rotational symmetry. So the number of times you can spin something and it ends up looking exactly the same as where you started. So if we have an equilateral triangle where all the sides are the same length, if I started that shape there, and then I spun it around so that this point is there, it would look exactly the same. And if I do that again and move this one to where that one was, and then again and move this one all the way around, that is 3. So including the last spin, I have 1, 2, 3 rotations there. So that is the order of rotational symmetry is 3. Now this is a correction I have to say. I was using a picture of my dog earlier and saying if the dog doesn't have any order of rotational symmetry, because I can spin any picture around and when it comes back, I've got exactly the same picture. But it doesn't really have rotational symmetry. So everything has a rotational symmetry equal to 1, but really we say that it's not meaningful. It's like multiplying something by 1. It doesn't change the result, so it doesn't have an order of rotational symmetry. So I'm going to give the line symmetry, and rotational symmetry for each of these shapes. So the line symmetry is, for a rectangle, we have this one, and we have that one. So it has two lines. This is a rectangle of symmetry, and no more than that. If I'm to rotate this, I could rotate this 180 degrees. And even though what was the top is now the bottom, the shape is exactly the same. So that's one order of rotational symmetry. And then if I flipped it back to look exactly as it did at the start, then I have a rotational symmetry of 2. If it was just a weird shape that I could spin around all the way around back to 1, we would say it has a 0. Would have no lines of symmetry. Now this one is a pentagon. And it is not only a pentagon, it's a regular pentagon. So a regular pentagon, if I put, say, a line there, I could fold those halves on top of each other. And I can actually do that a number of times. Where does that one go? From each corner to its opposite side. So a regular pentagon has 5 lines or axes of symmetry. And as far as its rotational symmetry, because it is an regular pentagon and all the sides are the same, each time I rotate one point to take the place of another point, it looks the same. So its rotational symmetry, if I spun it around, if I cut this shape out and spun it around a point, its center point, tree, is 5, because I can spin it around 1, 2, 3, 4, and then back to its original place, a total of 5 rotations.